sometimes we'll have functions where the second derivative test is inconclusive. So let's look at a couple examples. Find the partial with respect to x, and you have 8x cubed. The partial with respect to y is 4y to the third. Now the only way that these two partials will both be 0 is if x is 0 and if y is 0. So our only critical point will be the point 0, 0. So that's our only possible maximum or minimum. Okay, so now let's look at the discriminant. Remember, the discriminant is the second partial with respect to x times the second partial with respect to y minus the partial with respect to x and then y squared. So the second partial with respect to x is the derivative of the first partial with respect to x, which will be 24x squared. The second partial with respect to y will be 12y squared, and the partial with respect to xy will be the partial of this one with respect to y, which will be 0. So the discriminant will be 24x squared times 12y squared minus 0. Okay, so when you evaluate at 0, 0, the discriminant comes out to be just 0, which is the case where the second derivative test is inconclusive. Now let's actually look at the graph of this function. When you graph this surface, you'll see that there is a low point here, but it's very flat along the bottom. And when you have something where it's a very flat region, that lowest point sometimes gets hidden. So the second derivative test isn't able to detect that that is the lowest point. But you can easily see that if you looked at the point, you want to know what the lowest value this function f could have. It's going to occur when the x and the y values are both 0, because it's the sum of two terms that are both to even powers. So the minimum, local minimum and absolute minimum, is at 0, 0, but you had to look at the graph or just analyze that function to be aware of that. The second derivative test was inconclusive. Now the second problem, find the partials with respect to x and partial with respect to y. The partial with respect to x will be negative y squared, and the partial with respect to y will be negative 2xy. The only way that these will be 0, now for y squared to be 0, that means that y must be 0. But looking at the second equation, if the y has to be 0, the x here could actually be anything. So everything that satisfies this equation can have any x value. So x equal to any number, but the y is 0. So we'd be looking at critical points of the form a comma 0. So now let's look at the second derivative test. We have the second partial with respect to x is 0. The second partial with respect to y is negative 2x. And we have the partial with respect to xy. Take the derivative of this now with respect to y is negative 2y. So our discriminant will be 0 times negative 2x minus negative 2y squared, which comes out to be a negative 4y squared, which when you plug in the point a0, the discriminant comes out to be 0. So again, second derivative test is inconclusive. So now let's look at the graph and see if we can figure out what's going on. We're looking for maximums and minimum values. What's happening is when x is equal to a and y is 0, that means we're over the x-axis. So this is a little line up here that's hovering over the x-axis. So this is where x can be any value, but the y is 0. And that's the points on that surface. So if you look at the graph, that's g of a0. If you look at the graph here, you'll see that we've got a ridge there, and points over at this end, they have points. If you take a region around them, there will be points with that same z-value and points that are lower. But if you're looking here in the middle, you're actually going to have some points higher and points on the same level. So those points, none of those points are actually the highest point. There's actually several points there that would have highest and lowest. So they're maximum for part of the graph, and they're going to be minimums for other parts of the graph. So it's not something you can tell by using the second derivative test.